In this video, I want to explore the internal of diodes, which will also help me better understand transistors later. It's not easy to cover this at the right level. I could focus on the physics in a very hand-wavy way, which will not be especially helpful in building and analyzing circuits with diodes. Or I could go into the math, which could be to focus on calculations rather than application. This video is my attempt to find the middle ground and provide a mix of intuition and practical recommendations that you can use when building a circuit. I'll provide a simple mental model with practical calculations that work for many non-trivial applications. These calculations are designed to be straightforward and applicable, giving you the confidence to use them in your projects. However, for more complex tasks like alternating current or high frequency, you may need to explore other resources. Diodes are an application of semiconductors. Semiconductors have very surprising electrical properties. Let's compare it with an insulated wire made of a copper strand with a plastic sleeve. The copper core is a conductor where electrical charges can move around quite freely. The insulator has charges, like any material, but they are stuck in place and cannot move around. The only way to move charges in an insulator is to push them by applying a very high voltage of thousands of volts. That will get those charges loose and the current will flow. That's how lining flows through the air, which is an insulator. The process of an insulator becoming conductive at high voltages is called breakdown. Let's look at a semiconductor now, a pure silicon crystal. In a pure silicon crystal, charges are stuck, but just barely. So it still works as an insulator. However, when you add a tiny quantity as low as 1 part in a billion of impurities, many charges become loose. The impurities themselves are not conductive, they just affect the delicate balance between the stuck and not stuck charges inside silicon. Different impurities may get either positive or negative charges loose inside the silicon crystal. If the positive charges are the ones loosened, the impure silicon is called p-doped. If the impurities dislodge some negative charges, you have n-doped silicon. In both of them, charges can move, making doped silicon work as a conductor. So far, everything we have seen this semiconductor do is act like other materials we know, insulators or conductors. But if you have a piece of crystal and n-dope one side and p-dope the other one, then some magic happens. Sorry, I meant physics happens. I won't pretend I understand the quantum physics involved. Still, the consequence is that in the junction between both doped sides, called a p-n junction, the positive and negative mobile charges get attracted and get stuck together. There are no free charges within this region, and the current can flow the same way as in pure silicon. This zone, where charges used to be mobile but are now stuck, is called a depletion region or zone because it's depleted of mobile charges. This device is a diode. The p-doped side, called anode, and the n-doped side, called cathode, can be wired, and the junction will have different behaviors based on the voltage difference of both sides. If the p side gets connected to a lower voltage, in other words, the cathode voltage is higher, this voltage will pull positive charges in the anode towards the connection, and the same will happen in the cathode. This makes the depletion zone wider, so there's no current flow in theory. In practice, a tiny number of charges manages to get across due to the room temperature losing some charges and imperfections in the junction. That's what's called a leakage current, which is usually in the range of nanoamps for signal diodes or microamps for power diodes. A diode in this situation is not technically an insulator, but it's almost as effective. Blocking current in that direction is an everyday use of diodes. When the diode is in this blocking situation, we say it's in reverse biased mode. The other important mode is when the anode voltage exceeds the cathodes. In this case, the loose charges get pushed towards the depletion zone, and the stacked charges there get some pressure, the positive ones in one direction and the negative ones in the other. At a relatively low voltage, ranging from a fraction of a volt to a few volts, depending on the semiconductor, the depletion zone collapses, the loose charges become free, and you get a forward current flow. The diode is now forward biased. We can plot the voltage difference in the x-axis and the anode to cathode current as y to understand forward and reverse bias. To the left, the anode voltage is lower, and the plot shows a very low leakage current, close to zero. Now, to show you the positive side, I need to adjust the vertical scale. Towards the right, the current starts to slowly rise as voltage approaches to a forward voltage, where the current starts rising. After reaching that point, it grows very steeply with voltage, the same as a resistor with almost zero resistance. The forward voltage is a bit arbitrary. It depends on what is the forward current that we consider meaningful. But it's certainly not zero. There's a third mode going further to the left when the voltage difference becomes significant enough. There, charges get loose enough to jump the depletion zone like an insulator that breaks down. The voltage where this happens for each kind of diode is called the breakdown voltage. Depending on the diode model, it can be around tens or hundreds of volts. At the breakdown point, a lot of current can flow, and the plot bends sharply downwards. In most designs, this breakdown mode is undesirable. Most diodes aren't built to work that way and will get damaged in breakdown mode. Understanding the shape of this plot for each diode is the technically correct way to analyze diode circuits, but I'll show you some shortcuts to make things easier. Most diodes have maximum allowed currents both for the forward and breakdown modes. Too much current will overheat and damage the diode. Matching those with the voltage current plot, you get a complete bound for both current and voltages that you should keep the diode in to be safe. You must stay within the box to stop your diodes from catching fire. In practice, the voltage range where you have forward bias is very narrow, usually a fraction of a volt, and it's pretty tricky to control the voltage directly to keep it there, mainly because the shape of this plot will change with the temperature of the diode, so a safe voltage range at 10 degrees may not be safe at 40. The usual solution is to limit the current rather than the voltage. You can do so using a resistor like this. What I'm showing you is a collection of forward bias diodes across 5 volts and with different resistor values. By measuring the voltage drop across each diode, I can compute the voltage drop over its resistor, and with that, the current going through it. Instead of using the diode equation that describes the plot, you can learn to eyeball it, which often is all you'll need. The first simplification is based on noting that the voltage doesn't change much for different currents in forward bias. So you can just take an average value and treat it as a constant, which for most silicon diodes like this is 0.7 volts. Now you can skip the measuring and simplify the maths, even if you have multiple diodes. You count each diode drop as 0.7 volts, subtract that from your end voltages. In this demo, I'm using a 5 volt power supply, and divide by the resistance on that path. Suppose you only care about limiting the current below a specific limit, rather than knowing the exact value. In that case, you can take even more shortcuts. Don't subtract the diode voltage. Use the whole voltage to check what resistor you need. You'll end up using slightly more resistance than needed, but the diode will be safe. Very often, you can get away with this. In some cases, something else in your circuit provides a current limit. And if that's below the limits of your diode, you may get away without a resistor. A fun example is these coin cell batteries, which can't deliver a lot of current. I can connect them to an LED with no resistor and nothing will blow up. Don't do this with a power supply or a bigger battery. A couple of tricks can help you analyze and design circuits involving diodes. First, ensure all currents are appropriately limited, as we just discussed. Then you can assume the forward voltage as a constant. If you're using silicon diodes with currents in the order of milliamps, which is quite typical in digital components, you can assume the forward voltage to be 0.7 volts. The cathode voltage will be at least the anode voltage minus one forward drop. It cannot be below that because in that case the voltage drop will be very high and the current too high, but that's impossible because you started by limiting current as I told you to, right? In the same way, the anode voltage will be at most the cathode voltage plus the voltage drop. That gives you upper and lower limits for the voltages at different points of your circuit. If the diode is forward biased, the value will be the boundary. One of the diode connection is often at a known or fixed voltage, like the terminals of your power supply. In that case, you can use the previous rule to know the voltage at the opposite end of the diode. For example, if the anode of the diode 1 is connected to plus 5 volts and the cathode has some path to ground through a protection resistor and perhaps other components, it's forward biased, so its cathode will be at 4.3 volts. The cathode of D3 is connected to ground and the diode is forward biased, so the anode will be at 0.7 volts. Besides the power terminals, some other points in your circuit can have known voltages, like the terminals of diodes you already know. Again, in this diagram, you now know that the anode of D2 is at 4.3 volts, so its cathode will be at 3.6 volts. All these voltages are approximations, so if your circuit is affected by minor variations, you may need other calculation methods. I found it helpful to do this with a different notation to prevent having all of these strange numbers like 4.3 or 3.6. After all, these numbers were not exact anyway, and the numbers all change if I switch to a different kind of diode, like a Schottky with a smaller voltage drop or an LED with a bigger one. So instead of counting volts, I count diode voltage drops using arrows pointing up or down. An up arrow means add the voltage equivalent to a drop. For example, the voltage at the anode of D3 is ground up arrow. And given that up arrows usually start counting from the ground, I can omit the ground, so I'll instead say that the voltage at this point is up arrow. A down arrow means subtract one voltage drop. And unless I specify it, I can start subtracting from my top voltage, in this example 5 volts. So the voltage at the cathode of D1 is down arrow, and at the cathode of D2 is 2 down arrows. This seems silly, but it saves some arithmetic and we don't need exact voltages but just convert voltages on a circuit made with lots of diodes. It's enough. This notation will also be helpful later in analyzing circuits with transistors, which rely on p-n junctions as well, and will have similar circuit drops that can be represented with these arrows. Let me show you an example of analysis that showcases a design technique called current steering. Imagine you have two paths that the current could take that go over p-n junctions in diodes. The voltage drop in each path is different, and we'd like to know which path is taken. If the current takes the left path, the voltage at this point should be up arrow. If it takes the right one, the voltage will be 2 up arrows. The voltage can't be both, so it means that the current is taking only one path. Which one? Well, we know that this up arrow or double up arrow are upper limits for the actual voltage. So the voltage is at most 1 up arrow and at most 2 up arrows, which means that it cannot be 2 up arrows, it can be a single up arrow. In conclusion, current flows on this specific path, with this diode forward biased, and these two others are reverse biased. By analyzing with arrows, we don't really care about which kind of diode we are using, as long as all have the same drop. I've built this example with LEDs, and you can see that only the standalone one lights up. This example seems a bit artificial because if these two diodes are always reverse biased, you may as well remove them. But sometimes you have some dynamic element like a push button that can interrupt this path, and at that moment, that will enable this other path. So now a single on-off signal controls current flow over two different paths. That could be useful. In general, remember that if you have two paths with voltage drops, the current will take the one with the smaller voltage drop. Also, notice that in current steering, the voltage drop of the diode is not always an undesirable side effect, but something that we are using in our favor. Another example of the application of diodes is when you use diodes to connect multiple points at different voltages to a single point. Let's say the voltages here are 3, 5, and 10 volts. If you're showing all the cathodes, the voltage at the cathode is at least 3 down arrow, at least 5 down arrow, and at least 10 down arrow. So it must be at least the biggest of them all, 10 down arrow. Generalizing these examples, you can shine as many points as you like with diodes with a common cathode, and the common cathode will choose the maximum voltage minus a voltage drop. Putting the diodes with a common anode does precisely the opposite. Now the anode voltage needs to be smaller than all of them plus an up arrow, so the minimum value will be chosen. Computing maximum and minimums can be pretty valuable. You can use it for digital logic. After all, the logical functions and or are the same as maximum or minimum functions if you treat true and false as 1 and 0. In this case, the extra either up or down arrow can be a problem, so you must fix that. As part of my logic gate series, I've made an entire video about diode logic gates, so go watch it if you're curious. You can also use these maximum and minimum functions for analog and power applications. Let's say you have an alternating current, which looks like this wave, which flips between positive and negative with respect to this reference. And you want to make it closer to DC, a constant and always positive voltage. Using a maximum circuit between the wave and the reference, you can get this wave where you have removed the negative part. Then you could use a minimum circuit to get this other signal. If you now use the low signal as a reference, the total voltage is the difference that looks like this. It's not a flat line, but it's much closer, and some extra circuits can fix the remaining bit. This diode pattern is widespread in power supplies, and it's called the rectifier bridge. I hope these examples of diode applications have given you a few ideas about where to use them. I'll combine diodes and transistors in my next video to provide other examples. Before saying goodbye, let me review the key points we covered. Diodes are semiconductors with an N-side cathode and a P-side anode, and a junction in the middle that can change its conductive properties. The current flow depends on the anode-cathode voltage difference. It splits into three modes: forward, backward, and breakdown. Breakdown is usually undesirable. The circuit designer needs to limit the current through the diodes. Once limited, the voltage difference in a forward biased diode is almost constant, but this depends on the semiconductor used. Setting the voltage of the anode to a known value will give you a lower bound for the cathode. Setting the cathode voltage will give you an upper bound for the anode. You can often simplify the analysis of diode circuits by counting voltage drops instead of trying to get exact voltages. I write those as an up arrow or a down arrow. You can use diodes for their voltage drops or to steer current. Multiple diodes can calculate maximum and minimum voltages. This can have applications in logic or analog circuits. The p-n junctions of diodes also appear in transistors, and what you learn in this video will help you understand them too. As I mentioned before, I'm preparing another video about transistors, so I will see you then.